Today we have Professor Melinda presenting a GeoChat on ontologies. Ontologies formalize tribal knowledge and share semantics. Very lucky to have Melinda presenting. She's been on the vocabulary and ontology journey for quite a bit of time. You can see in the invite that she's got a really broad background both in academia and in the industry, and the engineering and manufacturing part of the resources industry. So we are quite lucky to have her present today and to share some of her insights and learnings from the journey she's been on in that space. Take it away, Melinda.
So first of all, I'd like to thank Klaus for extending this invitation. So as a maintenance reliability engineer, talking to a bunch of geologists is slightly intimidating. So I hope you come on the journey with me as we talk about what's appealing to me as a domain expert in terms of ontologies, and a little bit about the insights that I feel that I have got over the last 4 or 5 years. So because I'm a domain expert, and many, but not all on this call are likely to be domain experts, I'm really going to try and focus on this idea of formalizing tribal knowledge and being able to share in machine and human shared understanding of data. So let's see if I can get my slides to go forward. So I'm going to start with talking about this idea. I think we're all seeing what I call the data crunch. It's not my name for it. I'd like to acknowledge Tony Seal for this idea. But what we're seeing now is a recognition, especially driven by people's interest in AI models that rely on high quality data, rubbish in, rubbish out. But we know when it comes to our own internal data, generally, that we have a very fragmented data infrastructures. There's lots of proprietary systems. They're filled with poorly integrated and sometimes unverified data. And this presents a really major systemic risk to organizations if they start to want to do AI on their own data. And I was rather taken with Tony Seal's analogy of the 2007 financial crisis, just in the way that we package everything up and we make it look pretty and we pass it along. Are we doing the same with data, where we're sort of packaging it up and we put it on sites with BI reports, and the answers look fantastic, but underneath are the systems and the data that support the numbers that we're seeing, are they really robust? So it's probably appropriate with the financial industry in mind that actually one of the nicest web pages that explains ontologies, I think, to a non-ontology audience is in fact the financial industry business ontology. And I'm going to take a moment just to go through this page, because as we go through it, just substitute the word finance for your domain of interest: geology, geophysics, geochemistry, sampling, whatever it is. So this ontology, the fiber ontology, defines the set of things that are of interest in your domain and the ways in which those things relate to one another. This is like an English language definition of ontologies. The ontology gives meaning to any data in the domain that describes your domain. How does it do this? It represents a consensus on the common concepts as understood by the industry and the domain experts, and is reflected in your models, existing models, and the way you exchange data. It can be published. It should be published in certain specific formats. In this case, FIBO is standardized, and the FIBO ontology is managed by an independent, reputable third party. Really important. It's developed as an ontology in the web ontology language, which is codified by the web standards W3C. And it's based on description logic, a word I'd never heard of a few years ago, but this underpinning, and something you and I never want to touch. but it's a really important underpinning part of this world. And this use of description logic ensures that every concept in the ontology is framed in a way that is completely unambiguous and that is readable by both humans and machines. So there are some very key things that I hope I'm going to iterate on as I go through, but they come back to these core ideas. So I'm going to just, one of the first things that I was asked when I showed this to my geology partner was, oh, is there anything in the geology domain? And the answer is yes, and I'm going to tease you with this and move right on. So the key takeaways that I would like you to think about as we go through the next 35 minutes is, first of all, ontologies are hard work. You need to have a problem that needs an ontology as the solution. If you can do it any other way, have a look at that first. If you embark on this, then understand the roadmap. It's a lot of work, and you need to have all of this sort of infrastructure in place. For goodness sake, build on what's already out there. And I'm going to give you some examples of some things that I think might be of interest to you in your domain. Reiterating, use ontologies to formalize your tribal knowledge, whatever that is, where you need to do so. I've underlined the word ontology, and you can see I've got a couple of other underlines there. Those are the words, sort of the new language I'm trying to teach you or introduce you to, and I'm going to riff on these through the talk. I'm going to introduce the idea of modeling patterns, and these are really important. So many people who start with ontologies just think it's about identifying a few concepts, but this idea of concepts and how they relate to other concepts and how they relate to other concepts and how you do things with data in a pattern and a repeatable pattern is a really important feature that I think experienced users understand, but new users need to be introduced to. Probably one of the biggest things that's been a transition for me is this idea that all the data in an ontology, both the ontology model and all the instance data that you're using, is codified using URLs, using an address, like a web address, which we use all the time with the internet. And it's represented, everything is represented in something called the RDF, the Resource Description Framework. And I think this is probably one of the biggest transitions. If you come from the data modeling and the IT side, this is probably one of the biggest barriers for people. I'm not going to talk in the slides, but I'm happy to chat afterwards about other things that I think are worthy of this, but didn't really have enough time. Was, first of all, how do you find ontology experts? Because you'll need them. The emerging space where AI can help as you start to develop in your domain. And then something which I'm becoming increasingly vocal about, which is the need for government or associations and government agencies and industry associations to really step up and provide reliable and ongoing infrastructure for sharing this stuff. And this is one of the reasons I was keen to accept this invitation from GSW. So I know you're a bunch of geologists and you probably don't think a lot about valves, but I'm actually going to illustrate what I'm talking about with a use case that I'm working on for the resources sector right now, because I think it nicely encapsulates many of the points I'm trying to get across. So first of all, one of my first points was, do you have a problem that's big enough to do this? And in this particular case, the problem is that specifying valves on an offshore platform is a safety critical activity. When you design these platforms, you have to have engineers specify at least, sometimes as many as 8,000 valves. They all need a valve data sheet. Every valve data sheet references almost 100 standards, international standards, and it's an incredibly complicated thing to do. When you have a product that somebody might want to put on that and says, my product matches this valve data sheet, all of this stuff has to be checked by humans, by really experienced humans. Why? Because computers do not understand labels or concepts. They don't understand the concept of a size range or pressure. So if we want to support the human in this process through some form of automation, then we need machine interpretable data. And this is a big enough problem that quite a large number of organizations, including some of them you may have heard of, Equinor is the big Norwegian oil and gas company, energy company now, I think they call themselves, Aker Solutions, DMV, Able, and a big industry association called PCA, have been working on this for some time. And this is what the data looks like. It's horrendous. So we have the big colored bit is obviously an Excel spreadsheet, because that's what they do nowadays. Somebody says, oh, I want to buy, these are the specs for what I want to buy. And the product manufacturer says, oh, these are my specs. And somebody has to manually go through and go, well, yeah, do they match? What happens if the units are different? Da, 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 da. Top right-hand corner, we have text that comes from a standard, in this case, an American Petroleum Institute standard that defines what a valve is. And that's not exactly human readable, let alone machine readable. We have drawings with labels that we need to take in. Oh, that's what we usually call a valve stem, for instance. And then we have tables, which are incredibly complicated to represent. We're trying to represent temperature ranges at various pressures. And those funny codes that seem A182, well, that's a reference to a 200-page standard all by itself, which also needs to be codified. So this is an incredibly simple, this is not a complete set of steps at all, but I want to kind of give you some of the things that I think are really important to kind of grasp. I should say that my goal at the end of this is to make you curious about learning more, and hopefully some of the things will stick. I'm sure that some of the things will be, I won't explain very clearly, and I apologize in advance. But as we mentioned earlier, an ontology is you're trying to represent knowledge in a specific domain. In my domain, it's maintenance. In your domain, it could be geology, geophysics, whoever is on the call. We really need to start, I think, by deciding on what competency questions we're addressing. And in my experience as an academic, this step is often missed by academics, but it's not missed by industry. So what problem are we trying to solve? What is the questions, and what are examples of the answer? And why do I need an ontology to go from question to answer? If I can do that in an Excel spreadsheet or in some sort of query on a relational database, don't build an ontology to do it. And at the end, you need to go back to your competency question and demonstrate that the ontology will indeed answer it. So once we know what the competency questions are, we then look, well, what concepts are necessary in order to describe the data that will help me answer the competency question. And we usually, as a domain expert, we sit there on a whiteboard and we draw a little bubble, like I've drawn here, valve. Oh, I have a concept of valve. And I'm going to say, I've got a class of valves. And what are they? They're a type, subclass of physical artifact, like a pipe and a valve. They're all those, they're all subclasses of some sort of piece of equipment. We call it physical artifact. And then I need to say, well, they're connected in some way. And in this case, I'm going to give it a connection, important connection, called subclass, which is in ontology language, an example, it's called an object property. We also have data properties. And we do this, we, the domain experts, we do this. We need guidance and support because otherwise we go a bit nuts, but we do this. We then need to get the coders and the ontologists involved, because what they do is they take our, bubbles and lines, and they express them explicitly in what's called the RDF format, Resource Description Framework. This is a declarative language that has been around for as long as the web has been around. There is no shortage of materials. It's standardized. There's no shortage of materials about how to do this. But the upshot of this is it explicitly describes everything in your data model, because everything is given an address. And this is what my bubble diagram on the left looks like the code on the right, because it's going to be machine interpretable. It has to be written in code. And you can see, for an example, that my valve is in fact given an ID. In this case, the computer's given it an ID X10136838. And it's given it an address, which you can see in the, this up here. It's given it an address. And it says, oh, type, which is RDF, the subclass of the class valve. So I know explicitly what that is. I've used a couple of labels to say, oh, in human world, we might call that a valve. And by the way, it's a subclass of physical object. So this is an important thing to remember, is that ultimately anything, picture here, has to be represented in code. How you do that is really, really important, and there are rules about it. One of the things that I have really captured me in working in this space as a domain expert, collaborating in ontologies, is the opportunity to bring my expertise to the way these data models are built. And if you can't do that, or you're not going to do that, you might ask why you're building an ontology. Because the important thing about ontologies is they reason. They perform logical reasoning just the way that hopefully I might do it if I was doing it by myself, and I'm trying to provide the same sort of rules, for want of a better word, that I want the computer to use. And there are two important things here to be aware of. There are many important things, but two that where I actively participate are in the definition of class restrictions. So if I have a class valve, what does that mean to the computer? So if you look at the top right-hand corner, you can see I've got a valve, and I have created some subclasses. I've said a valve, something is of class valve if it has an assembled part, it's got a pressure retaining part, it has an inlet, an outlet, a closure member, and it's a subclass of physical artifact. Anything that comes in that meets those requirements is going to be classified as a valve. That's very useful. I don't have to, if I've made a mistake, and I'll show you an example of this later on, the computer will tell me, by the way, I think you've got a valve, a subclass of valve there. The other nice thing is that if this has these restrictions, everything that's a subclass of valve also inherits those restrictions. So that can be really handy from a data modeling perspective. It doesn't just apply to this class, but to everything that's a subclass of it through an inheritance rule. And the other thing is when we give the computer labels like has physical quantity, we can say you can only use this relationship if it's between a physical object and this class called physical quantity. If I mistakenly connect two things on my little bubble diagram that do not have those classes, the ontology will say, you cannot use that relationship between those classes. So this is this imposition of domain expertise, your understanding of the domain, into the way these things can be related. One of the, again, challenges I see when I review academic papers on ontologies is they're all about the model. Everybody wants to model the domain, but half of the papers don't have any data. So in my view, I suppose it's because I have a big foot in the industry world, the goal is not to model the domain. It is to model the domain to do something with that model. And to do something with that model, you have to have data, and you should have a competency question. Getting data into ontology models is a non-trivial step. And I think this is something where modern tools, and they have evolved rapidly, I think, over the last 5 years, have really changed this space. It's not an area I play in. I'm at the front end with the data, but magic happens now somewhere in between. And the magic in my domain happens with these things called otter templates, which are used to import data from all sorts of different things into the ontology. So we take data that might look like something below, and we can bring it into the ontology. This is a little example. I put quite a bit of information on the slides in case people want to use the slides later on, but this is an example of a particular individual. Purple in this editor. This is an editor for prototyping ontologies called Protégé. Purple indicates the instance data, and you can see that I have this valve. Essentially, it's an instance of this particular class of valve, and this tells me that at this particular part in the circuit, these are the operating conditions for this valve. I mentioned at the beginning this idea of modeling patterns, and as anybody who, I come from engineering, I'm like the Excel queen, you can just make CSVs until you're blue in the face. Somebody says, oh, I need to capture this, and you're like, okay, I'll make it a spreadsheet or whatever. Well, every time I do that or somebody else does it, there's a potential that we're going to label column headings differently, or we're going to model things differently. And this is a slightly complex example, but I'll try and walk it through. Say I have some data and I want to have the mass of a motor. There are many ways I could create my spreadsheet to capture this information. The most simple is to say, oh, I have a column heading equipment, and I have a column heading mass kilogram, and I have a number 20. Well, the ontology model for that is shown here, and the explicit code, the RDF explanation for this is down here. But what happens if I want to split up my mass value and my units? Well, then I have a different model and a different set of code. And what happens if I want to have this class that says, oh, there are different types of masses, there might be a motor mass, a pump mass, whatever, then I have a different model again. So this causes all sorts of problems for computers when you try and bring data together if you have modeled the data differently. So having modeling patterns, once you start to produce these, there are ways of aligning them, but having modeling patterns that you impose from a top-down perspective and make sure people use, and then check that they're using, and you can use something called shackle for that. This vastly improves the efficiency of the whole pipeline of work that you're doing. And I think this is patterns. We're beginning to see a call in the ontology community for people when they publish, not only to publish their ontologies, but to publish some of their key patterns. Patterns can be exchanged. These patterns can be exchanged. These are an artifact that you can reuse both within your organization and, if you're lucky, across different organizations if they're popular. So I mentioned earlier that you can do all sorts of data quality checks. Again, this is not exactly my domain. This is the domain of my collaborators. But one thing they're very, they find really useful is this feature of the RDF universe, which is called shackle. And basically think about this as being able to say at scale with one shackle shape, it's called a shape. It says, in this case, everything that is a unit of measure datum must have a unit of measure class, or everything that's a value must have at least one value in there, and that value must be a float. There were in this case two shackle shapes, and you can run them over the whole database and pick up problems. Obviously, you can do this in relational databases too, but this is the graph equivalent. One of the, I think for me, working in the industrial community is we have to work across different organizations. As I mentioned, the valve use case is a multi-organizational effort. If you want your ontologies to be developed and reused, like the maintenance ontology that I am one of the co-authors of, is aligned to two popular top-level ontologies. The reason a top-level ontology is essentially a grammar. It's like a specification in my world for a Lego brick. Think of a Lego brick. It has a certain size, has a number of interfaces, it has a purpose. If I want to go and build something and I don't have the Lego bricks, I can ask somebody else to make me some bricks, or I can make some bricks. But if I make some bricks and I don't conform to the specification, my bricks won't work with the rest of my bricks. This is the way top ontologies work. They impose rules on the concepts you develop and how you use them. And if, for example, you make something that doesn't conform, it doesn't have the same ontological commitments, you can't tie into one of the classes, the superclasses that are in that ontology, or find a home for your properties or your relations, then the ontology will throw an error. And when you run the reasoner. So obviously this provides modeling constraints. So people who like to just completely make up things by themselves, they don't like this. But obviously you don't get interoperability without constraints. Now, one of the great advantages of building to a top-level ontology is access to other modules that are also aligned to that ontology. So if you think about the picture on the right, we have a top-level ontology, and this represents what we use in the valve use case, we use something called the IDO, the Industrial Data Ontology, which is on its way to being an ISO standard. We then have these domain-independent ontologies because we don't want to go and work out what all the concepts for time or geospatial stuff or sensor measurement data or units of measure. We just want to import those and reuse them. In our domain, we're building the valve ontology. We sit here. We are making ontologies for the various industry standards that we're having to use. And then the individual companies are making ontologies, and then we bring in all the data at the bottom. So that I think that's really important, this whole bit of don't reuse, knowing what your competency questions are, seeing what's already out there in terms of existing ontologies that you can reuse, and then making sure how you can reuse them if they're aligned to a top-level ontology will save you a lot of time and heartache. So I talked also about the roadmap. This is sort of an overview of the valve ontology space, showing that, you know, essentially what we've got is we've got the engineering procurement houses here, we've got the operators who own the assets and are paying for everything, we've got the vendors who are supplying various valve products, and what we've done is we've created this blue space, this shared space where we exchange data models. But there are constraints on how the blue space is developed, and we are constrained by the fact that we have elected to go with the IDO top-level ontology. We have specified which of the domain-independent reference ontologies we're going to use, like the sensor network, units of measure ontology. We have made ontology patterns for the information in the standards, and we have developed templates which everybody has to use. And by doing this, once we've got set up, we can move reasonably quickly. I'm going to, these slides are a bit busy, but I just want, as I said, in the interest of making you curious about how some of this will work, I will do my best to indicate a couple of really cool and important reasoning capabilities that you get from ontologies. So the first one is inconsistencies. So, you know, I do a lot of work with industry, I get data from them, and I spend a lot of time trying to align that data that comes from different parts of business or different people who develop different things. So in this particular example, which I'm showing you, I'm bringing in data, and I've got two spreadsheets, and one says that a valve stem is a type of valve part, and another says, oh, a valve stem is a type of valve. But the problem is that we've said, as a domain expert, I've said, you know, something can't be a valve, it can't be a ball valve and a valve stem. A ball valve is a type of valve, and a valve stem is a valve part. So I've used my domain expertise to say these two things cannot be, something cannot be both of these things. So simple rule to put in, but it's fantastic because when I bring it in and I run the reasoner, I get this sort of yellow color that comes up on my protege, and I get the nasty appearance of the red text which says you've got a problem, and it tells me actually your problem is that these things are disjoint, so something can't be a subclass of both of these things. Fantastic. Imagine doing that at scale over hundreds of thousands of data entries, and you can see why I'm excited. A second thing also related to data input is inference. So I'm looking at two data sets, and I've got a data set where somebody said, oh, I have a fluid control object. And they've said, oh, fluid control objects have valve, a way of closing them. They have a valve part closure member. And so I bring in the data, and it says, so I've got fluid control object 101. This is a bit of data. And I've said, oh, a fluid control object class has a closure object, and it's a physical artifact. And when I run the reasoner says, oh, hang on a minute. I think your fluid control object is a type of valve, is a subclass of valve. Just check that with you. And of course it's right, because we've said also that if you have these rules, then you're a valve. And again, just think of being able to do this over extraordinary amounts of data. And this is an example of, a lot of work in terms of our competency question. I wanted to reiterate the value of having competency questions. So in our competency questions, one of the key things is if a vendor gives me a valve with all of its specifications and I have a valve data sheet, can I use the ontology to check that that valve example is indeed of that class of valve data sheet that we want it to be? And what we have done here on the left, you can kind of see a very high level structure of some ontology modules. So these are where these belong to the individual companies. This is the Equinor plant. This is the Aker BP plant information. We bring that data into what we call a valve collect, which collects a lot of valve information. We import the valve industry standards. We have the domain independent valve core. We have a piping core and a materials core. These are all shared amongst everybody. We have some other information that we need, and they all import IDF. So these are shared, and these are special to the organizations. And we can see that in this case, our snappily named OMS Salieri valve is indeed a subclass of this Equinor valve, and it is a subclass because it shares all of these same characteristics. This job for this particular individual task is this valve product. Can take as long as a day and sometimes two for a very experienced engineer to do. So this is, if we had to do it at a touch of a button, over 8,000 valves is going to be transformative. I did mention that scaling the process is, these things, we don't use Protégé, which is the package I've been doing screenshots from, is only for prototyping. You need full-on commercial things to be able to run the reasoning, store the graph, manage the versioning, and so on and so forth. So the world has exploded in this way, and there are not lots, but there are a number of key international providers that can assist. I don't deal with them directly, but I also within our community, within the Norwegian community, various groups, in this case DNV, have actually built tools, and I know of a couple of people who've built tools to help manage these the pipeline, so that domain experts like me can just do our bit, and the rest is kind of hidden from us, which I think is an important feature. So I mentioned that, look at what's already out there. There are geology ontologies. You might be curious to know that, in fact, GeoCore, which is shown in orange here, is in fact a BFO-aligned ontology. FIBO is a BFO-aligned ontology. That's a very big and popular community. The basic formal ontologies community is very big and popular for the natural sciences. There are also things obviously around things that everybody does, sampling. There's a semantic sensor network, the GeoSparkle for representing geospatial data, a time ontology. So there's a lot out there that I would strongly recommend you look at and think about reusing, and then only concentrate on what you need to do to move forward. So just to review, I'm coming up against time, so just to review my key takeaways. First of all, make sure you've got a big enough problem and the value you're going to get is going to be worth the effort. Understand the sorts of resources you're going to need. Build on what's already out there. The not invented here approach is not good for ontologies. On domain experts like me, this opportunity to participate and to help formalize tribal knowledge is fantastic, and I think it leads to much more business-focused data models. Modeling patterns are a good thing every way you look at it. I think it constrains people to doing things in the same way. You cannot have free will and ontologies. They're just incompatible. The ideas behind RDF graphs, some people I think will find that controversial, but RDF is declarative language, and unless you declare unambiguously what everything is, you will not get the interoperability that you want. And then if people want to chat about it, I'm happy to talk about the need for more ontology experts, some of the things we're seeing around AI, and then also my sort of current passion project, which is trying to get groups in the West Australian government to start to think about providing some of the infrastructure to store modules and ontologies and linked data and control vocabularies and all of that sort of stuff. So in finishing, I'd really like to thank many people who provide the grunt work that goes behind this, the ontology community, as well as other domain experts. And in terms of this, pulling this talk together for you guys, I'd like to acknowledge my husband Paul and my colleague Caitlin Woods, who are here in Australia, the whole of the Norwegian group who've been helping me with the slides, and Andreas Neumann in Germany. And also, for those of you who are interested, Caitlin and I manage a GitHub site where we put links to training materials of all types. So if you find that useful, let us know. But also, if you find something you'd like to contribute, please let us know too, because getting started in this space is not easy. Thank you very much.